What's up? Please pay no mind to the vampire costume. It's for a joke that starts in about 35 seconds, so. Anyways, my name is Galen Bergsten. I am a senior grad student at the University of Arizona, and today I'm here to share some work that I got to start a year ago when I was a visiting grad fellow here at IPAC and Caltech. I'll preface by saying that I'm not really a star person, so I've been learning lots of great stuff this week. This is the first time I've ever heard the word facula. I've been keeping track. I think we've said it 39 times, so let's keep it up. In fact, I've been counting facula so much, you might confuse me with Count Dracula. I am stuck in this costume for the next 11 minutes. Okay.
Sorry, who are you?
I hope that David will expense this $12 vampire costume.
That is not part of it.
Today, I'll be talking about exoplanet demographics and binary systems, but unlike the last speaker, I will not be talking about demographics of planets in binary or multi-star systems. If you want to learn more after that last talk, check out works by like Kendall Sullivan, Catherine Clark. They've got posters up this week. There's also some posters from folks like Dom Otto, Dan Fabricki, and Colin Littlefield that you can check out for different aspects of that problem. Today, I'll be talking about a technically different question of what happens when you do demographics on single stars that probably aren't all single, that there might be some unknown stellar companions lurking somewhere in your data. These unknown or unresolved companions cause all sorts of problems. One of the big ones we just heard about was this problem of transiting planet radii, right? So if you have a single star with a transiting planet, planet blocks out some of that star's light. That change in brightness tells you about its size. But if there's a second star in your image that you don't know about, then that can add in some excess light, which causes you to dilute the transit signal, underestimate the size of the planet compared to what is actually there. In a demographic sense, this causes some problems, especially in terms of detection efficiency. We heard yesterday in the demographic session, especially from Andatilla's talk, about how we are bad at finding planets. There are a lot of biases and things that we have to correct for in order to move from the observed population to the intrinsic population of what's actually out there. Detection efficiency is one of those, and it's a big one for the Kepler mission, which tells us how good we are at finding planets at different combinations of periods and radii. So say, and this is completely made up numbers, but that you are 10% complete to finding one Earth radius planet. So you could get one out of every 10. We'll now say that for some unknown chunk of your population, you have unresolved companions, which cause you to underestimate the planet radius, maybe by a factor of 50%. So for that unknown chunk of the population, you're more like 10% complete to a 1.5 Earth radius planet, a little bit less complete to an actually 1 Earth radius planet, and that mismatch causes all sorts of problems that you don't know about because you don't know how many stars this affects and you don't know how big of a deal it is. So when you go to calculate planet occurrence rates, which are already really hard to do correctly, now they are a lot harder to do correctly. The good news is that you can kind of fix this problem. You just have to go observe all 200,000 Kepler stars and figure out which ones have companions, but that's a lot of work, and I am a sad graduate student who doesn't have that much time. So instead, we're going to look at 200 of those stars and work with a control sample and see what we can do. So we picked a control sample of Kepler targets that we studied with adaptive optics, and in 40 of those systems found unresolved companions, things that had previously gone missed, stuff that we had once labeled single star systems, either because they were too faint or too close in that we couldn't resolve them. So now I'll tell you about how we used the properties of these companions and squished them into an occurrence rate framework to figure out how our occurrence rates, in this case specifically small planets, change when you add these corrections. So here is some old models of mine where we're looking at the frequency of planets as a function of their orbital period. We've got, I guess, 3 curves. There's super-Earths in blue, sub-Neptunes in orange, and if you add those together, you get small planets generally shown in white. So to start out, here are the properties of that companion sample, sort of your traditional imaging sample where you're better at finding things that are fainter when you get farther away from the stars. I don't want you to worry too much about these properties, but just know that they let us calculate these radius correction factors that Nathaniel was just talking about. So here is the probability distribution of correction factors from this sample, where most of the time you have like a 50% chance to have less than a 5% correction, but a non-zero chance to have something on the order of maybe 30, 40%. And this is just the example of things orbiting the primary star, but we also have to worry about that case where they might orbit the secondary, where things can be a lot bigger. So now the x-axis scale is showing from like 1 to 7, so there is a rare but still there chance of having your radii change by like a factor of 7, which is kind of a big deal. And so now that we have these properties from our companion sample, we can push them into our occurrence modeling framework and see how these corrections might change our occurrence rates. So we'll start with that original catalog of stars that we assumed to all be single and say, all right, some of these are probably not single, they probably have companions, but we don't know which ones. So we'll randomly assign those companions based on our observed rate of about 20%. And we don't know what the properties of those companions are, so we'll draw them from the distributions of stuff on the last slide. And then we'll use those properties to reevaluate the detection efficiency for that chunk of the population, and then put it all together with the rest of the single stars, reevaluate our occurrence rates, and see how everything changes. Let's start by looking at how the detection efficiency changes. So if you've never seen a plot like this, the color map and contours show Kepler's completeness, or like how good it is at finding planets at different periods and radii, where the 1% curve says that we could find 1 out of every 100 planets, and anything below that we get worse at finding. And so when you say a bunch of your stars have these companions, you have to correct for them and account for the fact that they are less sensitive to smaller radius planets. You can move those contours up, and on average, the shift looks a little bit like that, which in turn affects your occurrence rates. We went from the solid lines to the dot dashed lines, and you may be wondering, what's the difference? Those are basically the same curves. Why is Galen making a big deal about this while wearing a cheap vampire costume? First of all, rude. But second, I'm not done yet, because so far we've only been talking about the stuff that we could see, and there's plenty of companions out there that we weren't sensitive to. Here's a somewhat typical sensitivity curve. I sure can. Howdy, gang. Here's a somewhat typical sensitivity curve for Palomar adaptive optics observations, where we are pretty bad at finding things that are either really faint or really close in. And so we can use sensitivity metrics like this to figure out what companions might be lurking out there that we couldn't find. And here I want to credit Catherine Clark and Mike Lund for helping us with that simulation effort. So once we have those properties, we can figure out what their radius correction factors would be. For the purpose of this talk, these are mostly the same curve. But what's important is that when you add in the stuff that you missed, now you have more stars. And that helps us go from the 20% companion rate that we observed to the 45% companion rate that is kind of more typical of field stars. So, of course, when you have more stars to correct for, the correction effect is a little bit larger. So we get a bigger boost to the completeness, and in turn, a bigger boost to the occurrence rates, where now things are a little bit larger. But it's still kind of hard to see exactly what has changed here. So let's stop thinking in absolute space and now look at things relative to the models without companions. So here, the vertical axis will show you how the occurrence rate changes as a ratio between the models with and without companions. I'll start with the case on just the observed stuff, so that 20% only using the properties of things that we found, where there are two curves, one for super-Earths in blue, one for sub-Neptunes in orange. You'll note that the super-Earth curve is a little bit higher, and also that both of these curves tend to increase as you move towards larger periods. So there's two things here. First, that the increase in occurrence rates from these companion corrections gets bigger or more prominent for smaller planets, and planets at larger orbital periods or larger separations. The reason for this is because of the shape of Kepler's completeness contours, which have this curvature in the period radius plane, where you are generally less sensitive to things that are smaller and farther away anyways. So when you move those curves upwards, you have a reduced sensitivity to things that are smaller and farther away, which means that they get a bigger boost to their occurrence rates. Now, the one exception to this trend of generally increasing outwards is this weird squiggle that's happening at 10 days. And I'll tell you, it's not real. It's just a little bump that comes from, we're fitting a broken power law to these models. And in the case with companions, maybe the break at the power law is at like 10.1 days. And in the case without, maybe it's at like 10.2 days, which is not a big enough difference to be statistically significant or physically relevant, but it is enough to introduce a weird visual glitch like this. So don't worry too much about the actual shape of this. Just remember the trend that we get a bigger boost to occurrence rates for things that are smaller and farther away. We can say the same trends when we consider the full picture of the stuff that we weren't sensitive to. Having a bunch more companions, obviously there's a much larger effect on your occurrence rates, where on average, maybe you're getting something like a 20 to 30% boost in super Earths, with that being largest, like a 35% boost at 100 days. And for sub-Neptunes, it's a little bit smaller, maybe on the order of like 10, 20%. If you've ever heard any of my previous talks, you know that I can rarely go 12 minutes without talking about Earth-like planets or Earth-sized planets in the habitable zone. So let's take a brief segue and talk about those. So keep in mind this trend that things get, there's a bigger increase in your occurrence rates for smaller things that are farther away. Earth is a pretty small, faraway planet, at least on Kepler scales. So in this table, the A to Earth column is showing you the frequency of Earth-like planets. Our original models, assuming everything was single, had a value of like 8-ish%. Now we're going up to maybe 10 or 12% with these corrections. That's not a huge deal. Don't worry too much about these numbers. But what I want you to focus on is the column on the right, the relative increase column, because that is mostly model agnostic. So it's true for our values that we go from 8 to 12-ish%. But this is a correction that comes from just the shape of Kepler's completeness contours. So to the extent that your model is robust against those completeness contours, or that you model things at a high enough resolution, you can apply these correction factors to pretty much any occurrence rates for habitable zone things if the original study had assumed single stars. So maybe you don't like our value that says 8%, and maybe you like a model that is much more optimistic and gives you a value of like 50%, so 1 in every 2 suns could have an Earth-like planet. Well, if you add this correction factor, you can get a boost on the order of 1.2 to 1.4 times. That might push you up to something like 70%. So that's the takeaway I'll leave you with, that correcting for these unresolved companions can give you a boost to your A to Earth estimates by a factor of like 1.2 to 1.4. And with that, I'll close things off here, and I'd be happy to take any questions.
So, any questions for Dracula? Don't be scared. I don't think he bites. We're gonna start over there.
Thanks, Tim Benning, Sydney. So the example you have there on the left would have been resolved by Gaia, wouldn't it? Like Gaia can resolve to 2-arc second binary and would have 2 separate entries, not one with a single Rui like you showed on your other plots. Is that correct?
Yes, so some of these have been picked out by Gaia, and there are some that wouldn't, because maybe they're too close or whatever. We started this like a year ago, and I think 2-3 days ago, there was a new paper that came out basically looking at all 200,000 Kepler stars with Gaia DR3 insights, trying to pick out these companions, and they have some of the things that we found, but also not some of them. So there's still stuff that we can pick out with AO that we couldn't get from Gaia, and doing things in a uniform way like this is one of the things we need to do for demographics. So we could do it all with Gaia, and now maybe we will because someone else did that, but we could also just do this.
Elizabeth? Sorry.
Elizabeth Newton, Dartmouth. I was wondering, kind of following on that, have you thought about, I guess the paper was yesterday, so, but would it be advantageous to combine the Gaia constraints with the AO constraints to kind of better understand what you're missing?
Yeah, you could try, but it gets murky for demographics, which wants you to do, as uniform a thing as possible. So here we focused on a control sample and then made some statistical arguments for the broader population, whereas the Gaia stuff is sort of applied to the whole population. So combining those is sort of apples and oranges. There's still statistical ways to do it, but I think it's a lot more weeds than what we're trying to do, at least right now.
Do we have a final question over there?
Hi, Brajol from MIT. I was wondering if you have unresolved companion, how does that impact the stellar parameters we derive from SCD, for example?
That's a great question. So yes, so how do unresolved companions affect your stellar parameters and I guess in turn your planet parameters? The way that they usually do, which is that you're probably wrong first, so you try your best to figure out how you might be off, or at least put large enough uncertainties to capture that. So here, one of the things that we've done is using the properties of the things that we could observe, figure out what the sort of typical changes to your planet parameters are, and bake that in, but I glossed over it. But that's definitely a thing you have to worry about.
Okay, with that, let's thank Galen again.